Welcome to 9.2, series and convergence. Series and convergence. Okay, now this means sum. This looks like an E. This is the summation. Sum is n goes from 1 to infinity. That's the sigma, capital sigma. Of a sub n means we're adding up all these terms. So this is a summation. It's for a series. That's an infinite series, often referred to just as a series. When it goes from 1 to infinity, that's an infinite series. The terms of the series are A1, A2, A3. The sequences we talked about in 9.1. So it's common to write an infinite series as the sum of a sub n. So sequences of partial sums, S1 equals A1, S2 equals A1 plus A2. This is a partial sum. That means the first term, first two terms, the sum of the first two terms, sum of the first three terms, sum of the first n terms. Definition of convergent and divergent series. For the infinite series here, n goes from 1 to infinity of a sub n. The nth partial sum is given by s sub n equals a1 a plus a2 all the way through a sub n. If the sequence of partial sums s sub n converges to s, then the series sum converges. So if the partial sums, if you look at those, the pattern of all those partial sums are going to a specified value. That's where the series, the infinite series, is going to go to. So the limit s is called the sum of the series. The sum is a1 plus a2 plus a3 all the way through all the terms. Now let's be realistic. We can only do so much in addition. We can't do a million terms. We can't do an infinite number of terms. So we can only do what we can do. So we're going to be looking at patterns here. That's what this is all about. The rest of this chapter is finding patterns to find these series. They converge, they diverge, and different rules. Okay, so telescoping series, if the partial sums diverge, the overall thing diverges. So telescoping series, kind of cool. B1 minus B2 plus B2 minus B3 plus B3 minus B4 plus B4 minus B5. It's whenever these terms will start canceling out on themselves. So that you have a minus B2 and a plus B2. You have a minus B3 and a plus B3, minus B4 and a plus B4. So these things are going to cancel out. And you'll end up with plus b sub n, comma b sub n plus 1. So all these things will cancel out in there. And you'll be left with like the first term. Okay, let's find the first 5 partial sums. Hope we're good with our adding fractions. So our S1 is just going to be 1 over 2 times 3, which is 1/6. S2, that's going to be 1/6, plus the next one we can reduce that, 2 and the 4. That's going to be another 1/6. Then we have 3 over 20. Oh no, that's just the first 2. That's right, we're done there. So that's 2/6, which is 1/3. S3 is going to be 1/6 plus that 1/6 plus. Then we have 3/20, and that'll be approximately 0.4833. S4 is going to be 1/6 plus the 1/6 plus the 3/20 plus 4 over 30, and that gives us approximately 0.6167. And I'm not seeing, I mean, this is decimal form. What is 1/6, isn't it? 0.11, it's a 0.06. This is 0.33. But we don't see it, I don't see it really tapering off yet. S5 is going to be 1/6 plus 1/6 plus 3/20 plus 4/30 plus 5/42, and that's going to be approximately 0.7357. So all they're asking here is for us to find the first 5 partial sums. We've done that. I don't see a great pattern here, but that is what we're asked to do. Okay. A geometric series, I talked to you a little bit in the last section about an arithmetic series. This is a geometric series. The sum then goes from 0 to infinity of a times r to the n. It's a plus ar to the 1, ar to the 2, ar to the 3, plus dot dot dot, ar to the n, and so on, as long as a is not 0. That is a geometric series. The point of geometric, it goes up by, each term is multiplied, the previous term multiplied by a common thing, like r is the ratio. So a times r is ar. AR times r is AR squared. AR squared times r is AR cubed. We're multiplying by something every time. In an arithmetic series, you're adding the same thing every time. This has a common ratio. Arithmetic series had a common difference. Okay, a geometric series with, this is a typo, ratio. R diverges if r, the absolute value of r is less than or greater than or equal to 1. So if your common multiple is bigger than 1, absolute value is bigger than 1, it's going to diverge. But if your common multiple, the absolute value is between 0 and 1, it will converge. It will converge to the following. Sum and goes from 0 to infinity of ar to the n is a, this number around here, over 1 minus r. So verify that the infinite series diverges. So in this case, the common ratio, your a is 1 in this case, common ratio is 4/3, which is bigger than 1, so it diverges. And the next one, we have n over n plus 1. A1 is 1 over 2. A2 is going to be 2 over 3. A3 is going to be 3 over 4. A sub 0 is going to be just 0 over 1. That's just 0. Okay. The limit as n goes to infinity of n over n plus 1 equals 1. So in the long run, we're going to have the sum of this n over n plus 1. It's going to be 1 plus 1 plus 1 plus 1, an infinite number of times. So that means this diverges. Before we go to example 3, I need to move things up. Okay, verify the infinite series converges. We have this series n goes from 0 to infinity of 0.9 to the n power. And if it's expanded there a little bit. So our common ratio r is 0.9 in this. That's the thing that's raised to the n power. 0.9 is less than 1. Therefore, the series converges. What does it converge to? The sum as n goes from 0 to infinity of 0.9 to the n power is going to be a is just 1 here over 1 minus 0.9, excuse me. It's 1 over 0.1, which is 10. So it converges to 10. That was a fun one, I think. It's kind of cool. Theorem 9.7, properties of infinite series. If the sum for A sub n is capital A and the sum for B sub n is capital B and C is a real number, then the following series converges to the indicated sums. The sum as n goes from 0 to infinity of C times A sub n is C times what it sums to, at capital A. The sum as n goes from 0 to infinity of A sub n plus B sub n is just the first series sum plus the second series sum. And the sum of the difference of these series is the difference of their sums. 9.8, the limit of the nth term of a convergent series. If the sum as n goes from 1 to infinity of A sub n converges, then the limit is 0. I want to be careful here. If the limit is 0, it does not imply that it's convergent, though. That's an important distinction to make. This is an if-then statement. The if part is if the series converges, then the limit is 0. It's important to note that the converse, as I was just saying, is not necessarily true. To test this, see the harmonic series. And the harmonic series says this. It's the sum as n goes from 1 to infinity of 1 over n. That's 1 plus 1/2 plus 1/3 plus 1/4 plus, this is divergent. It's a divergent series that diverges. However, the limit as n goes to infinity of 1 over n is 0. So just because the limit was 0 doesn't mean it will converge. So what is true is if it converges, then the limit is 0. So you've got to make sure you pay attention to the order there. Okay. Moving to the next page. Theorem 9.9, the nth term test for divergence. If the limit as n goes to infinity of A sub n is not 0, then we know it diverges. So that's a little different than what we saw before. If you're into logic and proofs and stuff, this is the contrapositive of the previous statement we saw. So it says, if P then Q, this is if not P then not Q. Okay, find the sum of the series. Use a graphing utility to find the indicated partial sum S sub n and complete the table. Okay, now this is, you can use the TI-89 for this. And I'll tell you about that in a second here. So when we're using this on the TI-89, you want to do the F3 button and choose the sum. So you're going to do the sum, parentheses, 6 divided by, and we're going to use x instead of n, x, now do parentheses, x times x plus 3. So look at the number of parentheses. I have 1, 2, 3 open, 2 closed, then comma. X is the variable. So you got to say now this is the argument, this is the variable, and you're going from 1 to 5. So in that first case, you put that in there, you're going to have 2.798. Then you can do it again. The nice thing about the TI-89 is that you can just call it the previous entry you made and change it to a 10 instead of a 5. And in that case, you're going to have 3.164. So look at the sum. What's going to happen with it? You think it's going to level off? Put 20 in there. 20 in there, you're going to have 3.394. Yeah, it looks like it's kind of slowing down the increase. Put 50 in there. 3.551, and put 100. 3.608. So if you're graphing this, 10, 20, 50, 100. And we have 1, 2, 3, 4. Okay, so 5 corresponds to 2.798. 10 corresponds to 3.164. 20 corresponds to 3.394. 50 corresponds to 3.554. 100, 3.608. So we definitely see it's kind of leveling off here. Okay. And the limit, by the way, as n goes from 0 to infinity, no, I think we have to go from 1 to infinity. As n goes to, sorry, not limit, the infinite sum as n goes from 1 to infinity of 6 over n times n plus 3 is going to be 3 2/3. You can get that by doing a partial sum with that. Not partial sum, do partial fractions. Okay. I need to move that up now. May have to switch to a black pen soon. This blue is getting kind of light. Okay, find the sum of the convergent series. Sum as n goes from 1 to infinity of 4 over n times n plus 2. So we have the sum as n goes from 1 to infinity of 4 over n times n plus 2. Now we can do some partial fractions here. If we said 4 over n times n plus 2 equals a over n plus b over n plus 2. Remember from chapter 8 we did partial fractions? If you forgot, you can go back and look at that section. I think it's 8.7. Could be 8.5. It might be 8.5. So that's going to be 4 equals a times n plus 2 plus b times n. So if n equals negative 2, 4 equals a times negative 2 plus 2 plus b times negative 2. So 4 equals negative 2b. B is negative 2. And if n equals 0, 4 equals a times 0 plus 2 plus b times 0. So 4 equals 2a. A must be 2. So what we're seeing then is the sum as n goes from 1 to infinity of 2 over n minus 2 over n plus 2. So if we started listing these out, this is where it gets really interesting. It becomes like a telescoping series. So we have 2 over 1 minus 2 over 1 plus 2 is 3. Plus 2 over 2 plus, or no, minus 2 over 2 plus 2 is 4. Plus 2 over 3 minus 2 over 5. Plus 2 over 4 minus 2 over 6. I don't know if you see a pattern yet here. But here's the fun part. Minus 2/3, that's gone. Minus 2/4, that's gone. These will be gone with future terms. So all you really have is 2 over 1 plus 2 over 2, which is 3. And that is the sum of the series. I think that's kind of a fun one, the way things collapse like that. Go on to the last page for this section. Now here's some skills that you, excuse me, you may have done this before. You may not have kind of put this all together. But this is kind of a neat way to write a rational number. Remember, rational numbers are numbers that repeat or terminate. This is a repeating number. It's a rational number. That means it could be written as a ratio of two numbers. It could be written as a fraction. Okay, so write the repeating, and by the way, fractions, like 4 halves is 2. 4 halves, which is 2, is a fraction. Okay, write the repeating decimal as a geometric series, and write its sum as the ratio of two integers. So what we have is 0.99999. That's 0.9 plus 0.09 plus 0.009 plus 0.009, no 3 zeros, plus 0.00009 plus, so that's 9/10 plus 9/100 plus 9,000 plus 9/10,000 plus 9/100,000. So I hope you see a pattern here. If my first term is A, my common ratio is 1/10. 1/10 times 9/10 is 9/100. 1/10 times 9/100 is 9,000. 1/10 times 9,000 is 9/10,000. We can represent this as the sum as n goes from 0 to infinity of our A, which is 9/10 times R, which is 1/10, to the n power. So that the final sum is going to be A over 1 minus R, which is 9/10 over 1 minus 1/10. It's 9/10 over 9/10. And now this is going to blow your mind. We're talking about 0.9 repeat. What is 0.9 repeat? It's 9/10 over 9/10, which is 1. I know that's something we never learned before, never were taught that. It's kind of a cool result that 0.9 repeat is going to be 1. I think it's kind of fun. Okay. Let's scroll this up to our last example of this section. Find all values of x for which the series converges. For the values of x, write the sum of the series as a function of x. So we have the sum as n goes from 1 to infinity of 3x to the n power. So this is like a geometric series where a is 1. So the r is the thing that's to the n power. R is going to be our 3x. And the absolute value of 3x must be less than 1. So that absolute value of x must be less than 1/3. And if it helps, I should start this over because this says n equals 1. Here we go. We could write it like this. N goes from 0 to infinity of 3x to the n plus 1. So if n is 0, starts at 1 like it does there. Now, you can take this a step further and say n goes from 0 to infinity of 3x to the 1, 3x to the n power. And this 3x to the n then will be a geometric, and your a is the 3x here. So a equals the 3x there. That's how it should have been done because n needs to start at 0. So your sum is going to be a over 1 minus r, which is 3x over 1 minus 3x. And that's your sum. Okay, and that'll do it for 9.2. Let me know if you have questions, and we'll see you online. Thank you.